Okay, and throughout this course, we are only looking at what are known as open link manipulator. What that means is if there is a base, then the manipulator is something like a serial link. So the end effector is connected to the base through a link structure like this. This is different from a closed link or closed link manipulator, which are something like this. Okay, so there is somewhere in the manipulator's space, there is a closed chain. So what we'll do is we'll only study these manipulators in this course. Okay. So these manipulators, the left ones, actually more common than the ones on the right. And if you're curious, one example of a closed chain manipulator is the Stewart platform. Okay, we will not study those. So let's see how to figure out the kinematics of open link manipulators. So in general, here is a schematic of such a manipulator. There's a link, and there's another link. And here I'm only showing revolute joints, but it can be some other joint, could be a universal joint, gimbal joint, whatever you have in the case of the manipulator. And so keep going. Somewhere there is a link, it's called this link I. Of course, this is link 1, link 2, so on. There's a link, it's called that link J. Eventually, the last link is our link N, or this is also known as the end effector. End effector is where you might want to put like a gripper so that the gripper can go and grasp into objects in the space. Okay, so we'll also have a certain convention for joints. We will call this joint as joint so this one is joint 1, joint 2, joint 3. So for link I, we would call this link as, so this joint as joint I, joint J, and of course this last joint is going to be joint N. Sometimes people like to also name the ground with a express the ground as a link. So let me just call that link 0, which is basically the ground link. Okay. Occasionally, manipulators are the ground link, or the link 0 is not actually the ground link, but it is actually connected to, let's say, a wheeled robot, and so the link 0, which in this case the ground link, is actually moving. So that's also possible. And we'll not focus on those kinds of robots where there is a wheeled robot connected to a open link chain. Okay, so that's the caricature. And what we'll do is, this is where we're going to tie what we've learned so far when it comes to frames. We'll actually have coordinate frames attached to each joint, and that will help us to describe the kinematics. So for joint I would have an axis like this. So this is my frame xi, yi, zi. For link J, which has joint J, we would have xj, yj, zj. And the real power of using those homogeneous transformations, which we talked last time, is they will seamlessly help us to describe how this link, for example, the end effector, moves with respect to the ground frame, which is our fixed frame. So this is x0, y0, z0. So in other words, what we'll write is we'll write these transformations from j, so link j with respect to uh, frame I, okay, where I can be, well, I've just shown you generic I and j, but it could be I could be 0, I could be 1, j could be 0, j could be 1, and so on. So we need to be able to write this formula down in order to figure out the kinematics. So the formula for hij, if I is less than j, so this is the scenario here, the I is less than j, because if you start numbering from 0, then link I will occur first and link j will occur after that, so I is less than j. The formula for the transformation from frame j to I is I plus 1, I plus 1, I plus 1, I plus 2, and so on till h j minus 1 hj. Okay, and what is h? H is the homogeneous transformation, and we've seen how to write the homogeneous transformation for rotation about x, y, z, and translation about x, y, z. So it's essentially that same thing. So this is the homogeneous transformation. Okay, so that's I less than j. If I equals to j, which is you're trying to find the homogeneous transformation of the link with respect to itself, then that's simply the identity matrix. Okay, is 4 times 4 identity matrix, because the transformation is really unity, because link j with respect to itself is simply the same thing. And then we have, what if I is greater than j? In this case, so you're trying to find what is the position of this link with respect to the link which is forward, or forward in the kinematic chain. Here what we do is we actually use this trick, which is hij times hji is identity, and so you get hji inverse. Okay, so you find this transformation and then you inverse it. Okay, so that is sort of the starting point for transformations. Okay, any questions so far? So now is where we'll get into the actual convention used for describing the kinematics. And there are numerous ways of finding for finding the expressing the kinematics. So for example, when we talked about rotation matrices, we saw that we can write Euler angles, and then there are I believe 12 combinations, right? Rotation about x, y, z, or rotation about x, then z, then y, and so on. So there are 12 ways of doing that. Same here, you can have multiple ways of expressing these transformations, but the convention will stick to, and which is kind of very popular in robotics or manipulator community, is known as the Denavit-Hartenberg convention. Denavit. Okay, and this I think is important because if you sort of open the manual of any robot, then you will see that they will give you a particular table which expresses these numbers, which are actually Denavit-Hartenberg parameters. If you know those parameters, then you can actually recreate the kinematics of the robot, and you can use it for inverse kinematics, motion planning, whatever you want to. But it's important to know how this convention works. So the Denavit-Hartenberg convention is a way in which we are keeping fixing these axes onto the joints and using that to keep track of the kinematics. So the H matrix is something which comes from this convention. It's basically four transformation. First one about the z-axis by an angle theta, and I'll tell you what theta is in a bit. And then there is rotation about, well, translation about z-axis by distance ti. Then there is translation about the x-axis about ai, and then there is rotation about the x-axis by alpha I. So if you go back to the H I wrote down in my previous class, you can actually write down the formulas for these H's. It's pretty much the rotation and the translation put together in this special 4 by 4 form. So I'm going to use some shorthand notation now, and I'll just I'll put the notation, I'll write it in that notation and then tell you what I'm really putting down here. So this might look slightly strange to you when I write S theta and C theta. C theta I 0, 0. Okay, so I wrote this because I'm going to write C theta I as basically the cosine theta I. It's just makes my life easy when I write these things down. S theta I is nothing but sine theta I. Okay, and so on, as we'll see. So then we have the translation about the z-axis by distance di. So that's going to be, first we write the identity matrix for the first three rows and three columns. Then we have translation about the z-axis by distance di. So I'll be that di here in row 3, column 4, and then zeros for the x and y translation. Okay, looks like I'm going to run out of space. Okay, so let's continue writing the third transformation. So this is translation about the x-axis by distance ai. So all I need to do is go to the fourth column and write ai for the x element, and then 0, 0. And the last row is simply 0, 0, 0, 1. And finally, we have rotation about the x-axis by an angle alpha I. So that is going to be uh, the rotation matrix for about x-axis. So I'll write it as C alpha I, S alpha I, 0, S alpha I, C alpha I, and then 0, 0, 0, 1, 0, 0, and 0. That's because the translation about the x, y, and z due to the fourth homogeneous transformation simply 0. So again, what is C alpha and S alpha? C alpha I is cosine alpha I, and S alpha I is sine alpha I. Okay, so I wrote this down, and these parameters, theta I, ti, alpha I, and ai are the Denavit, are the DH parameters, which you should see if you open the manual for some of these complicated robots. Okay, now one thing to note is we talked about how do you express the position and orientation of an object in space. Well, we need three numbers for positions, right? X, Y, Z, and three numbers for rotation. So alpha, theta, and psi. That's what we used. Six numbers. But the DH convention says we only need four numbers to express the configuration of a manipulator. So there is sort of a conflict, right? How can we get away by defining only four numbers when there actually needs to be six numbers? The reason why we have four in DH but not six is because the way we define the axis of the manipulator helps us to get rid of two parameters. Okay, and that's why we have this, complicated, as you see, way of writing this, because it simplifies the number of numbers we use to describe the manipulator. So let me just make a note of this. This is 4 numbers to describe each link. However, we know that it takes 6 numbers. So it will be x, y, z, theta, phi, psi to describe position and orientation of each link. So we get away with only 4 numbers as opposed to 6 because DH uses a special way of defining the axis of each link. So what is the special way? Well, the special way is actually two things which DH does. One of them is, the first thing it does is it says that the axis xi is perpendicular to zi minus 1. So that's the z-axis of the previous link. And then the second thing which DH does is it assumes that xi is intersecting zi minus 1. Okay, so that's the other thing. So it's two constraints sort of, which reduces 6 numbers to 4 numbers and helps us to describe the manipulator kinematics. So I'm going to basically this is just for information. We will, like, I'll actually show you how to figure out the DH parameters quite easily by showing an algorithm. So this is just for information. If somebody asks you why it's 4 not 6, then that's the answer. Now I'm going to basically uh, show you what these two assumptions really mean. Okay, so this is taken from the book by Spong. Okay, it's one of the reference books. You do not need to actually go and buy it. Okay, so this is showing two adjacent links, link I and link I minus 1. So remember that this is the earlier link, this is the later link. So joint 0 or the ground link is somewhere here, right? And that's the end effector is here. This is sort of the opposite of what I drew earlier. So this is zi minus 1, and then this is zi, and this is, you can barely see this, xi. Okay, and so this is basically saying that the two assumptions were xi intersects zi minus 1. So this one intersects zi minus 1, and then xi is perpendicular to zi minus 1, which is shown here. So this is assumption, or rather, this is number 2, and then the intersection, put it this way. So this is the 90 degrees thing which I showed in 2, and then this, the intersection which is shown here, is number 1. Okay, and you frankly don't need to draw this any point of time. It's just for a reference. So these are how the parameters ai, alpha I, di, and theta are defined. Okay, ai is the distance between, so it's shown here, ai is the distance between zi and zi minus 1 along xi, and so on. Okay, and I will actually be using this later on, but uh, if you think my explanations in this class where I'm going to show you how to do this is hard, then you want to go back to this figure and read this. But let's just move on for now. Okay, so what I'm going to now show you is how to use DH convention in order to put down this axis, which is the most important step. Once you put down the axis on the manipulator, that is at each joint, then we generate the DH table, which will have these four parameters for each link. Once we do that, that's the second step. The third step is very trivial. It's just taking that H matrix, which I wrote down, which has those four multiplications, and then getting the transformation for a particular link, and then just putting these H's for each link to build the kinematic chain for the whole manipulator. So there are three steps. Step one is the hardest, probably, because it's about defining the uh, axis. Step two is also similarly hard, but then step three and everything else is very simple. So once you have those two steps, everything becomes easy. Now I'm going to actually, I just took it from Spong. This is the algorithm from Spong. I also shared this handout with you in Blackboard. Okay, what I'll do is in some time before I actually start doing problems, I'll actually send this handout again through the Zoom chat so you can have it and see through it as I solve problems. So as I said, essentially three steps. One is assign coordinate frames. Okay, there are four possibilities here, and we'll go through these possibilities in detail when we solve problems. I don't want to talk about these because they won't make no sense to you at this moment. Okay, so that's the first step. This I would say is the hardest one. The second step is to generate this DH table, and the DH table is generated by looking at the axis and using that figure I showed you, AI alpha, DI theta, that figure I showed you some time back. That figure is used. So I'll populate these numbers, four numbers for each link. So if you have n links, there'll be n times 4 parameters. So that's the second part, which is probably slightly less hard than the first one. And then the final part is writing the H for a particular link. And so this formula comes from the formula I wrote earlier. It basically is H about Hz about theta I. When you take the multiplication, you get this formula, Hx AI Hx alpha I. So that simplification comes to this. And once you have the parameters, it's just a matter of putting the numbers in this equation, which MATLAB can do for you, and then getting the transformation of frame I with respect to the previous frame. Okay, so that's easy. The final step is we want to find the position and orientation of the end effector. So again, imagine this manipulator. It has these links. Finally, there is an end effector. That's your link n, and this is your link 1. Okay, so this basically is a transformation from link n to, well, this is 0. It basically tells you what is the position and orientation of this link with respect to frame 0, or this is the fixed frame. Okay, so when you do this multiplication of these h's, and you will have n of them because there are n links, you will actually end up with this really simple form. There's a rotation matrix, which is a 3 by 3 matrix. There's a translation matrix, which is a translation vector, which is 3 comma 1, and then 0 and 1 doesn't matter. So this is a 4 by 4. And so the orientation of the end effector is simply Rn0. Okay, and then the position of the end effector is simply Dn0. So all you got to do is actually just read off this H matrix. The 3 by 3 matrix for the rotation is the orientation, and then the vector for the last column is going to be the translation, and that is telling you how the end effector is oriented with respect to the fixed frame, which is this frame. And why are we interested in doing this? Uh, since most times manipulators are manipulating or grabbing objects in the world frame or fixed frame, we want to know this transformation, else the manipulator will not know where to move in order to pick objects, right? Because we describe objects in the fixed frame or the world frame. Okay, so that's sort of the introduction to DH.